Welcome everyone to the Maui Institute for Astronomy. I'm Dr. J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist here. And one of the things I get to do is bring incredible speakers like Paul to come and give these presentations. We give them about once a month, and if you're not on the mailing list and would like to be, we do have a sign-up sheet, and possibly also you can just poke me in the, when we're out in the foyer and get me to add you to the list. This month's speaker is Dr. Paul Schumacher. He currently is working with the Air Force Research Labs Space Surveillance Systems Branch, so that's the local branch of the Air Force Research Labs. He works on cataloging satellites, and he has 30 years of experience with this. He's been with the AFRL for 10 years. Before that, he spent about 17 years with the Navy Space Surveillance Operations. And his degrees actually all come from Virginia Tech, where he majored in aerospace engineering and specialized in orbital mechanics. And so he'll be talking about the future of the space satellite catalog, and let's give him a nice Maui welcome.
All right. JD, thank you very much. Thank you. And thank you all for coming. I had no idea the room would fill like this. Maybe you just always fill it up every month. I'm not here every month, but I certainly appreciate you coming out tonight. Okay. I want to give you some basic facts about a subject that doesn't often come up in astronomy circles or people that are connected with astronomy somehow, which I assume everyone here is here at the Institute for Astronomy. Nevertheless, this subject is one that will get to be better known in the future as the satellite catalog grows, and I'll explain what that means in a minute. The importance of it also grows. And whereas now, if satellites collide in space, it hardly makes the news. In the future, that will be different. We'll all be much more aware of what's going on in space. Hence, my work at Air Force Research Laboratory is in so-called space situational awareness. We're trying to get ready for that future, which is going to be way beyond our grasp if we don't do the work now to figure out how to take care of this situation. This is supposed to be an introductory talk on the satellite catalog. I'm assuming nobody's ever even heard of such a thing. You might know that satellites orbit the Earth, but that may be all you know. And I certainly don't want any of you all to be left behind by this talk. This really is 101. If you have a question, raise your hand, or if I'm standing in the light here and can't see you in the dark out there, just sing out, and we'll try to make sure nobody's left behind. I will give you some insight into the fundamentals of why there's a catalog and so forth, and about something called the SSN. You'll have a lot of acronyms in this talk tonight. SSN means Space Surveillance Network. That's the government's designation for a system of satellite tracking sensors worldwide, and I'll tell you more about that later, which report tracking data to a central location where it's turned into a database that we call the satellite catalog. So another question that comes up is, how big is it now and how big is it going to get? Right now, we'll get into this more, it's a few tens of thousands of satellites. In the future, we may be dealing with a few hundreds of thousands of satellites, and not the too distant future either, for reasons that I'll describe. Building that big database turns out to be mathematically hard in an engineering sense, and just hard logistically, in fact, in some respects, hard to comprehend. So I will have something to say about that, and we'll all walk out of here with some level of expertise in that subject. Then we'll make some conclusions and leave time for questions if y'all are still with me. Not too many people know that the job of maintaining current awareness of all trackable space objects is the job of the U.S. military. Right now, that job is done by the United States Strategic Command. It's a joint service command. All branches of service are involved in this business. And it started out as a military job back when Sputnik was launched in 1957, October 4th, I think, October 57. And since then, the U.S. military has been involved in this. Because to this day, the U.S. military has most of the sensors, most of the radars, most of the telescopes capable of doing the job, they still are stuck with the job, although it's not entirely a military activity. It supports a lot of civilian activities, as we'll see. The current database has a list of about 22,000 objects, more or less. This number fluctuates. It's been over 23, it's been down to 21, but because satellites come and go, new ones get launched, some satellites re-enter the Earth's atmosphere and are no longer in the catalog and so forth. But we're talking in the order of 22,000, more or less, at the present time. Yes, they all circle the Earth. They're all in orbit around the Earth. As I said, not too many people are keenly aware of this fact. It's a huge job, and it will get much huger in the future, which is why I'm taking up your time tonight. Of those 22,000, not all do we know everything about. About 15,000 of the ones that are in the current catalog are known pretty completely, what they are, where they came from, and so forth. In particular, we can associate a country of origin with those objects. Now that's important because the United Nations Treaty on the Peaceful Uses of Outer Space, which was adopted in 1965, allows international reporting, in fact requires international reporting of space objects. But if we don't know the country of origin, we can't put it in the UN report. That's an interesting situation. The U.S. military has 22,000 objects in the catalog, and the UN thinks there are 15,000 in orbit around the Earth, more or less. These numbers fluctuate again. But that leads to some very interesting situations. From a military point of view, if you don't know the national origin, it's especially interesting, perhaps. Whereas for most civil purposes internationally, that doesn't matter too much. Most people also don't know that only about 5%, or perhaps even less, of that total list of objects consist of active satellites. Satellites actually doing a mission. Satellites receiving commands from Earth, providing data to the Earth, only about 5%. The other 95% are completely inert. They consist of those satellites that have run out of gas, run out of juice, broken down, or just exceeded their useful life. They are dead payloads in space. Every time you put one of those satellites in orbit, you also put the upper stage of the rocket in orbit right behind it. That rocket stage can stay in orbit a very long time, and typically does stay in orbit about as long as the satellite. Not only that, sometimes satellites blow up. Just as often, upper stages of rockets blow up, perhaps years after they were injected into orbit, because they have a little residual fuel. Over time, the radiation from the sun heats up that residual fuel in the tank, and the tank bursts. That's happened a number of times. And so you have a lot of debris, fragments, shrapnel, if you will, in orbit around the Earth. A lot of that debris we can track. It's big enough for radars to pick it up, telescopes to see, and we have to keep track of that. I'll get into that more later. Why do we have to track this 95% of stuff that is junk in space? That's a very important point that I'll get back to. Very seldom, but occasionally, satellites collide with each other. Now, of course, it's we've always operated in space on the big sky, little airplane theory, if you will, little satellite theory. Space is very big, satellites are very small compared to space, so that the chances of two specks hitting each other flying around in space are not too great, except that those satellites are moving at tremendous speeds, and they sweep out a lot of volume over time, so it doesn't take too long to sweep out the entire volume that all the satellites are traveling through, and greatly increasing the chances. Some satellite will hit some other satellite sometime, and that problem will get worse over time. There is a mission of somehow characterizing that population of space objects that's not trackable by the ordinary, mostly military radars available to us. And that job devolves on NASA. In particular, NASA Johnson Space Center has an entire office, a few people, dedicated to the job of somehow monitoring and characterizing that population of space objects that we know are there but which we can't track routinely. They have various means to sample that population and to model it statistically and to try to estimate what the risk is from collision with those very small objects. And I'll get in a little bit more on that later, because the military, the U.S. Strategic Command Catalog per se, feeds into that debris risk assessment job at NASA, which goes on behind the scenes all the time. A lot of uses for the catalog. When Sputnik was launched, the military suddenly realized they had a use for a catalog. Several uses, in fact. The Navy happened to realize, as soon as Sputnik was launched, that, by golly, all their ships at sea can now be seen by satellites from space and might be under surveillance as a satellite flies over. That meant that the U.S. Navy was suddenly deprived of one of its traditional strategic advantages, namely surprise. It's too hard to watch the whole ocean if you're using normal terrestrial means, and so they had the advantage of surprise. They could locate lots of ships, lots of firepower where they wanted to, and no one would know it till it was too late. But with satellites in orbit, everybody knows where they all are all the time, and that was a problem for the Navy. So they realized they needed a catalog to know when certain satellites were overhead of certain ships on the Earth, and that job goes on today. At the same time, the Air Force realized that if there are satellites orbiting the Earth, and a very fast-growing number of them, not too many at first, but fast-growing number, they realized they had a problem with the ballistic missile early warning systems that were in place. If a satellite transits through one of those radar system coverages that is supposed to detect incoming intercontinental ballistic missiles, you need to know it's a satellite and not a missile, otherwise you're going to blow the horn and start a war, and it wasn't supposed to happen. So they had a problem. They needed a satellite catalog so they could predict when satellites were supposed to be seen by these systems so they wouldn't trigger a false alarm. Very important. And it worked, by the way. We haven't had nuclear war since that system went into place. Many other uses here. And over time, the uses tend to, while these military reasons for keeping a catalog have always been there and are still there today, the uses of the catalog, as you list it over time, become more and more civilian in nature. Very interesting development. For instance, NASA Johnson Space Center, NASA JSC on this chart, is very concerned about manned space flight. And during the entire shuttle program, they were doing special operations depending on the space catalog for advance notice when an object might approach the shuttle or later the International Space Station. They needed to know this far enough ahead of time to be able to move the shuttle or the space station out of the way, not to get hit. Turns out almost any collision in space is near catastrophic. We'll get into that later. But for NASA, that was a clear and present danger. They spent a lot of money, took a lot of time, and a lot of people to this day are still employed in the business of alerting the International Space Station to close conjunctions. They have to know about 72 hours in advance that a close approach with another satellite is going to happen. That's a big job. I mean, 22,000 satellites that we know of, you got to check them all against the space station all the time. And then as time went on, NASA Goddard Space Flight Center, GSFC on this chart, decided to start doing the same thing for all the NASA unmanned missions. All the scientific satellites, all the geophysical observatories in orbit around the Earth are monitored for close conjunctions with other satellites. The reason is not because of risk to human life, but risk to economic assets. Those satellites are expensive to replace. They provide very valuable data. You don't want to lose any of that or have to expend efforts to replace it. So they take very good care to move unmanned satellites out of the way now. Now, as time went on, U.S. Stratcom was called into service to support commercial entities. There are companies that operate systems in space, and they want to know if they're going to come close to some other object. Remember, only the U.S. military has the resources to do this monitoring mission. So naturally, it devolves on them to alert satellite owner operators if something bad's about to happen. That happens routinely now. Now, of course, it's not the U.S. military's main job. They would like to pass this off to somebody else, but meanwhile, the U.S. military is keeping the catalog. So it's an interesting situation. We are currently in process of developing some well-defined data sharing techniques with our allies. Who are our allies? That's another discussion in itself. We won't get into that in this forum. However, it's a very serious discussion, and just in the last year, I've been in a number of meetings on that very topic. The problem with that is, how do we share data worldwide with our allies without giving away our own strategic advantage for knowing what's going on in space? Should we just give all that data away? That's a deep discussion, and it's being worked. There's a worse problem lurking out there, though, a strictly civilian problem, which is international space traffic control. No one's got this even well defined yet. But I've been saying several times here that the issue of avoiding collisions in space is a big deal. NASA spends a lot of money, time, and people doing that job. The military is concerned about it too, but that's less of a high-profile thing. But now we're talking about tens of thousands of active satellites in space in the next few decades. Yes, the population may grow exponentially if certain projections are correct. And what that means is people are going to start getting in each other's way a lot more often. Who decides? Who maneuvers and gets out of the way? Who decides that? It's an international problem. It's not analogous to the air traffic control, where if an airplane is within someone's airspace, it's that country's traffic control problem. In space, first of all, airspace only extends up to 50 or 60 miles. Above that, it's international waters, like the open ocean. Satellites go around the Earth in an hour and a half. They fly over every country on Earth. So it's an international problem inherently. Whose job is it in each country to make sure that there's traffic control? Who alerts who about what sort of circumstance? Who's allowed to launch when so they don't endanger anyone else? That is a job that's presently being worried about, but not being worked very effectively at the moment, to be honest. I've been in some meetings on that subject in the last few years, too. Very unsatisfactory overall, I don't mind saying, because the DoD is presently doing that the best it can not to interfere with its primary mission of national defense, but at the same time, the Department of Transportation and the FAA, who normally might be expected to pick up this job, are pretty short on satellite experts. So it's a generational problem, probably. It'll be solved at some point, somehow, and however it is, it will be an interesting business. This is the Space Surveillance Network, a cartoon of it, if you will. Yes, ma'am. Yeah, they're on a new orbit. Yeah, that's right. And in fact, by maneuvering out of the way of one satellite, you might be lining yourself up for a collision with another satellite later, and you're going to have to find that out right away. You see the problem here. It gets really complicated really fast. Yes? Yes. Absolutely. Yes, thanks, JD. The question is, as we launch more small satellites like CubeSats, which are basically pretty hard to detect, okay, they're right, CubeSats are 10-centimeter cubes, and a lot of university science departments like to build these things and have them launched as just free hitchhiking rides on bigger boosters. A lot of that's going on. The problem with CubeSats is you can barely see them in a surveillance sense, and they can't maneuver for the most part. There's no command and control. So you've just put a lot of shrapnel in space as far as everybody else is concerned. What are you going to do about that? Whose job is it to protect the commons, the space commons, if you will? We don't want to get into the so-called tragedy of the commons, which you hear about in some environmental reports and dissertations and so forth. Yes? I'll get to that. Yeah, Joe's asking about the Space Surveillance Telescope. It's actually Morón, Spain, Morón Air Force Base. Yeah, you're forgiven though, and you still get full credit for the question. It turns out that particular one is not there because we want to replace it with a much better optical system. The budget being what it is, you have to take one away first before you can put another one in its place. But we're going to get a much better optical system somewhere else in the world from the Morón. The Space Surveillance Network is probably the largest tracking network ever built that wasn't designed. Okay, it was not designed to track satellites for the most part. Only a few of these systems the red dots you see up there are dedicated to the space surveillance mission, whether they were all designed for that or not. Most of them were. The yellow dots are basically radar systems that were designed to do ballistic missile early warning. Remember I said that was one of the big concerns at the beginning of the space age. Those yellow dots are mostly the BMUs sensors. If you can remember back in the 50s, BMUs was getting built. And still is in operation, by the way. Been upgraded many times over the years, but still does the job. Of course, not too many missiles are flying. The missile detection sensors are mostly tracking satellites on a 24-hour basis. There are some other sensors up there that do other missions. Some of them are university affiliated, like the Millstone radar is affiliated with Massachusetts Institute of Technology, Lincoln Laboratory. And some of them just are very, some very esoteric missions, some of them intelligence related. On Maui, let me walk over here. On Maui, we have two systems. One dedicated telescope system called the Maui GEODS, Ground-Based Electro-Optical Deep Space Surveillance System. And the green dot there is the so-called Maui Space Surveillance System. It's a research facility. It's our Air Force Research Laboratory systems that can be pressed into service on demand to do space catalog-related things. So it's Maui's a big player in this business, and always has been. You notice, well, this world map doesn't show it too well, but we're basically Maui and this so-called Reagan test site on Kwajalein Atoll in the Marshall Islands are the only Pacific sensors. And that's a very important area of responsibility for the United States Strategic Command. We have possible adversaries in Asia, for example, just for example. And the satellite business in the military point of view precedes everything else. Satellites give you your situational awareness in space and on the Earth. So there's that. So this is a very motley collection of sensors. Some of them have colorful names, pretty exotic names, but they're all just tracking as many satellites as they possibly can all the time. There's a couple of dozen altogether. They come and go periodically. Sometimes budget forces you to turn one off. Sometimes they're obsolescent. You need to replace them with something else. We have several new sensors coming online in the next 5 to 7 years. So some of those dots will go away and other dots will appear. But it's about that many sensors doing the job over time. Okay? Here's a snapshot. This is a snapshot of the catalog probably about 10 years ago. Now this is just the UN, this is the UN catalog, the 15,000 objects that we can associate with a country of origin, and this is just the low Earth portion of them, okay? So this is a little more than eye candy. It is a snapshot of the positions computed from the catalog database and plotted on a three-dimensional graphic and displayed on the chart, okay? But it's about 10 years old. We've got more than this now. The catalog is a little more dense than that in the near-Earth environment. If we is the same for each satellite, remember they're not as big as the pixels on this chart, but there are that many of them. Okay. You see the low Earth orbit regime, so-called LEO regime, just really clouding the Earth a lot. You can also see, at least from the back of the room, you might be able to make out this ring. We're seeing an oblique view. The North Pole is about here, so we're seeing an oblique view. This ring of satellites here is in the equatorial plane of the Earth. Those are the geosynchronous equatorial satellites, GEO satellites. And in between the low Earth orbit and the geosynchronous orbit are all of these medium Earth orbit satellites. That's the rough classification of where they are by altitude. And so you see there are quite a few satellites everywhere. Yes, sir. Yes, there are a few beyond the ring. Now, there are not very many. And now, to answer your question, let me go to the next chart. This is looking down on the North Pole. Okay, now in this view, the North Pole is right in the middle. You still see the low Earth orbit population, and you see the geosynchronous orbital belt here. That's an orbit regime that is probably the most valuable real estate in outer space that there ever will be. Because a satellite in this particular orbit goes around its orbit at the same rate that the Earth turns. So these satellites are stationary in the sky and are used for television, for example. Okay? DirecTV, many, many other things. The weather satellites are out there. Yes, sir. It turns out that there are a lot of satellite orbits in LEO, low Earth orbit regime, that fly over the poles. And so those orbits naturally cluster together over the North Pole. And so that's not an optical illusion. At any moment in time, there are a lot of them over the North Pole, and the South Pole likewise. That's correct. That's correct, yes. So I'm talking to a more expert audience than I thought. Yes, sir. Yes. How wide is it? Yeah, that's a good question. The question is, how do you, essentially, I think the question is, how do you do traffic control in this geosynchronous orbit? Everybody wants to be there because having a satellite stationary over your ground territory, valuable thing. The UN and the International Telecommunications Union parcels out longitude slots for these satellites. The operational satellites are assigned a longitude, and they pay good money to get it. And the country near the equatorial region on the Earth, directly below that longitude slot, gets a say in who goes in that slot. So, for example, the king of Tuvalu has some say over what goes over his island in the Pacific. Yes, sir. Essentially none. One. But they can be close together. They can be, a hundredth of a degree apart, but they can't interfere with each other. If they're close together in space, they have to be far apart in frequency for telecommunication purposes. So it's a complicated business parceling out this ring. Now, the question might follow logically, what happens when those satellites go dead? So usually a 10 or 15-year design life. What happens when they run out of fuel, run out of juice, break down, etc.? What has been done up to this point in time is, when your geosynchronous satellite nears its design life, you want to move it. You want to move it up above, that is, out from the Earth, up above, and put it in an orbit outside the geosynchronous belt. So when it goes dead, it won't interfere with what's going on down between these satellites and this geosynchronous orbit and the Earth. It's been moderately successful. Most companies and countries try to do that voluntarily, but there are some problems with it. Okay, I probably don't have time to get into that during the talk, but I'm happy to go into that with you later. Yes, ma'am. Okay, so it goes to a lot of places. Yeah, that's right. There's an international bureaucracy for telecommunications, and some of it goes to that. Mostly, it goes to other companies because they collaborate with each other to design the communication systems. Usually you don't have one longitude slot. Usually you want a satellite here, here, here. If you have 3 of them 120 degrees apart, you can just barely cover the whole planet. You want more of them to have some redundant satellite coverage, but yes, it's a big international collaborative enterprise, and there's a lot of money changing hands. Yes. This is just the known satellites, and in fact, it's just the known satellites we can assign a country of origin to. Remember, that's only about 2/3 of what's in the game here. We're tracking a lot of things that we don't know where they came from. If they're active, we can usually figure it out, but if they're just a dead piece of stuff in space, and we didn't find it until it went dead, then, well, we don't know where it came from. Very seldom can we ever figure that out. Okay. Let's go back to the oblique view here. I've been saying a lot about radar sensors for keeping the catalog. I've plotted pretty carefully to scale on this view the practical limit for the radar range for surveillance of satellites. If you don't know what's there and you just need to scan the sky with radar, you can see about this far out. That's about go from the center of the Earth to the Earth's surface, 6,000 kilometers more or less, 4,000 miles. You can go about that high out into space, roughly 5,000 kilometers, before the radars just can't put enough power out there to get the return back. Okay, that's the effective radar surveillance volume. Now, if you know exactly where the satellite is, you can put a radar beam on it, and you can pump energy on that one spot for a few seconds or minutes, and you can get a return. But in a surveillance sense, you can't do it. If you don't know what's there and you just want to find out, that's about how far out you can do that. We're in the current catalog, the lower limit of detectability is right at 10 centimeters characteristic size. That's that CubeSat size I was telling you about. Now, that, of course, means that you're not seeing all of those objects. You're seeing those with some probability of detection, and that probability is not close to 1 necessarily, okay? The details of that are essentially still a military-sensitive subject. But in fact, we don't have anything like a complete inventory of 10-centimeter objects. We've probably got a pretty complete inventory of 30-centimeter objects, like roughly a foot in diameter, in low Earth orbit. But above that, above this red line, farther out than that, we do not have a complete inventory even of 30-centimeter objects. Okay? I'll revisit that subject in a later slide, so if I don't, get all the ramifications for you, you ping on me again. Okay? Thank you. Now, this means that we got to use something besides radar. The answer is telescopes, optical surveillance. And that's what our Maui facility does, optical space surveillance, developing techniques to use telescopes. Because with a telescope, you don't have to pump energy out there. You're looking at reflected light from the sun. The sun's very powerful, it lights up everything. So even if something's pretty small and far away, you have a chance of seeing it with a telescope if you're looking at the right time and the right place. Telescopes, of course, don't have a wide field of view, typically a fraction of a degree, a degree or two. But for space surveillance, you need a whole lot of telescopes to do this job, okay? Now, let me pose a question to you, if you haven't already posed it to yourself. Why do we need a catalog? I mean, I've said some of the reasons why we're doing this. I've given you some hints along the way. But the question is, why every detectable object? Why do we have to have a catalog that accounts for every detection of every space object that we can make? In other words, why does the catalog have to be complete? Why does it have to be timely? Why do we need to know right now what's there? And that's a serious problem. We get a lot of tracking data. We got to convert that into orbital information and predictions of other satellite positions within minutes at most. Okay, we need to know right now. And why does it have to be extremely accurate and extremely precise? Why can't we just get away with some slop in these figures for where satellites are? Why can't we just do this statistically? In other words, why track every fish in the sea? One of the advantages of working for the Department of Defense, the way I've done for 30 years now, is that every once in a while you get to brief a general officer. Okay, that's an exciting affair, typically. One of the disadvantages of working for the Department of Defense is that every so often you have to brief a general officer. I had a 2-star general ask me this question in front of company one time, okay, in a briefing. And this general was moving from one assignment to another. He stopped over in Maui on his way to his new assignment. I should say she. I'll tell you the name afterwards. Very perceptive, technically brilliant, I would say. Some general officers really know their stuff. This general said, why do we try to track every fish in the sea? Isn't this unnecessary? Why don't we just track the satellites we're interested in? Why do we have to keep a catalog continuously? Why don't we just build a catalog every time we need one? Just build it from scratch every time we need one. Okay, well, you think on your feet pretty fast in a situation like that. And I did make an answer, a very respectful answer, but let me expand my answer to the general a little bit. We need the catalog to be complete, accurate, and timely, and there are quantitative requirements that the Department of Defense works to for these characteristics. We need to know what our operating environment is so that we can plan continuously. If you think life on Earth is complicated, life in space is very complicated. Things are moving really fast. There's a lot of them, and it's hard to know everything that you need to know at one time. But we need awareness of that entire operating environment before we can make rational plans about what we're going to do next in space or in some respects on the surface of the Earth. You need to make those decisions fast enough to support the situation when you might have an emergency or at least some time-sensitive problem. Now, much of this is military in nature. I don't want to get into it. But you can imagine, suppose the shuttle was disabled in orbit. Okay, you've got hours to a day or so to pull the astronauts off of that shuttle. Nowadays, the space station can go a little longer, but if they're disabled, maybe something's damaged and you may have hours to a day to get the guys off the space station. How are you going to plan that kind of operation if you don't know what's in orbit near the space station? That kind of thing. You need to be able to handle that. If you have a catalog, you can predict what the situation is going to be. Okay, if it's complete, timely, and accurate, you can predict what your satellite situation is in the neighborhood when it comes time to pull off that operation. Now, stuff goes wrong in space all the time. Satellites flake out. Even cosmic rays can interfere with the electronics on a satellite, flip a bit, so to speak, and change things, destroy things, break things. When something like that happens, you need to know whether this is something that nature is doing to us, or whether it's inadvertent, accidental, or whether humans are doing something deliberate to us. That's part of that military function I was talking about. But you have to know your entire operating environment to be able to draw valid conclusions about why did this just happen. Okay? The main reason for most civil purposes and commercial purposes is that you need high mission reliability. And this was my answer to the general who asked me, why do we need to track every fish in the sea? It's because in space, even a 1-pound trout can sink your ship. Yes, sir. That is correct, and I can give you the numbers. The question is, the reason the 1-pound trout is a danger to a ship is because it's moving at tremendous speed. Okay, that was the question or comment basically, and that is correct. In fact, the average relative speed among satellites. Remember, you have to go in low Earth orbit. You're going about 7 kilometers a second to stay in orbit, but they're going in all different directions. So the average relative speed of satellites is more like 10 kilometers a second. Sometimes they're going head on, that's 14. Sometimes they're going sideways, that's 7 times square root of 2, that's something. But on average, over the whole satellite population, it's about 10 kilometers a second. Okay? At 10 kilometers per second, a 1-pound trout has the same kinetic energy as a 500-pound safe traveling at Mach 1 at sea level. Okay, that's what the gentleman was referring to. I mean, you can make up your own scenario, but all that energy is going to go somewhere if it hits you. And you just had a very bad day in space. Even a tiny piece of aluminum, a millimeter or two in diameter, will have the same kinetic energy as a 16-pound bowling ball at 60 miles an hour. Okay, this kind of thing. That's why space debris is a big deal. Okay. Now, if you want to have high mission reliability, there's no other way to do that but just track everything you can possibly track. Okay. And the sensor systems that I mentioned that will be coming online in the next 5 to 7 years are capable of tracking very much smaller stuff. Right now, the lower limit with our UHF band radars is around 10 centimeters. We're going to be going down to several centimeter scale kinds of detections routinely, at least for low Earth orbit. Yes, ma'am. Was there a question here? Okay. Yes. Yes. Mm-hmm. Oh, the question is, what effect does this space environment have on the Earth environment, if I may put it in those terms? The answer is there is some, but it might not be what you think. The main hazard for us Earth dwellers is that some of that junk will re-enter the atmosphere and it won't all burn up before it hits the ground. Every day, 2 or 3 pretty large objects re-enter the atmosphere. If it's bigger than about a square meter in typical size, some of it's going to hit the ground. You may remember back in the 1970s, I don't know if you're like me, that's getting far enough back, but the NASA Skylab vehicle fell to Earth. It was about a 200-tonner, okay? It came down over Australia, and large chunks of it hit the ground on a sheep farm, turns out. Didn't hurt anybody. I don't think we've actually lost life, human or animal, yet from debris. But that hazard is there. Right now, we have the International Space Station in orbit. Design life goes out to about 2024, maybe 2029 if you stretch things. But NASA's going to have to put that thing somewhere when it's done. Right now, the easiest trick is to deorbit it at a controlled time and location so that it falls in the Pacific Ocean. Okay, that's the NASA solution. So you can think that's going to have to be very carefully planned. So yes, there are environmental effects. It turns out in the United States, we're less concerned about this re-entry hazard than people in Europe are. In Europe, you hear a lot, in Europe, space satellite community, you hear a lot about the re-entry hazard. Well, yes. Right. It's monitored continuously. And in fact, all close approaches of satellites to one another are monitored in some respects. We attempt to predict as many as we can. We screen conjunctions, as we call them, all active satellites against the space catalog pretty routinely, but there's also the issue of one empty rocket body hitting another and creating shrapnel in space that wasn't there before. That issue is definitely there. The main Earth effect will be that if a satellite we depend on economically or logistically gets damaged by debris in space, suddenly we're out of business on the ground. You can't swipe your card at the gas pump. You can't tune CNN. You can't do a lot of stuff until that satellite gets replaced or fixed. Well, right now, the sky's the limit, ma'am. How many is too many? We're going to find out in the next few decades. Okay, that's why this issue of the future space catalog is a pertinent one. Yes, sir. Any question? Yeah. Yes. That's happened a couple of times. The ones that I know about, I'm not sure about a Chinese vehicle. There was a Russian vehicle. Started out at launch, it was on its way to Mars, but it went into low Earth orbit and got stuck there, loaded with toxic fuel. And it was the Phobos Grunt satellite vehicle, and it had a lot of fuel still on board because it needed to make that next burn to go to Mars. Well, got stuck in low Earth orbit. The Russians went to fairly extreme lengths to make sure they could deorbit that object over the ocean, where it was less likely to cause any harm. There was another case some years back that was actually pretty close to home here. You can find the open source news about it, but a U.S. satellite went into orbit and was in a similar situation. Toxic fuel on board, also some sensitive electronics and stuff like that. So the U.S. Navy was called on to destroy that satellite before it re-entered, which they did with a ship off the coast of Kauai. Aegis cruiser sent a Standard missile and turned it into small pieces instead of one big piece. So those all burned up on the way in. So you know, the surface of the Earth is what it's all about for us. And so anything that happens in space may have sort of unexpected consequences for us on the planet. Okay, so I'm not going to dwell on this. I just wanted to point out that building the catalog or reconstituting it from scratch is not only the largest tracking problem in history. I mean, nobody's ever tried to track that much stuff all at one time. It's also one of the most difficult kinds of tracking problems where you have no a priori information and you need to just build up all your information from scratch. You need to do it fast. Okay? There exists today no sure method to do that. The result being that the U.S. satellite catalog, the U.S. Strategic Command satellite catalog, if it were lost, if all copies of the database were lost and we had to start from scratch to build the catalog, we could not do it in a reasonable amount of time. Because the satellite has been built 1 and 2 satellites at a time, gradually over the years since 1957. If we start from scratch now with everything that we can see, there's not a computer system available, there is no software available to build that catalog in a reasonable amount of time. It could be done, but it would take years. And that's one of the reasons why there's a research effort going on, including my little group on Maui, is concerned with this kind of thing. I'll have more to say about that later. I want to help you understand the difficulty of this tracking problem. I said it's the most difficult category of problems. Here's what you get into. Everybody knows baseball, right? Everybody been to a baseball game or at least seen kids play or something like that? Okay. In baseball, you have 1 baseball and 3 outfielders, okay? Normally, if you hit a baseball to the outfield, those outfielders can handle it. I mean, even in the majors, once in a while, the guys miscommunicate and it falls right between them and they lose the play. But in general, that's pretty easy. Now, what if you had 3 baseballs going out to those 3 outfielders simultaneously? Now you got a problem. This is suddenly complicated. The guys have to communicate with each other. Somebody's got to be in charge or it's going to be kind of, you know, every man for himself. How do you label the balls? How does one player know how to say, that ball is the one you're supposed to catch and that ball over there is the one I'm going to catch? How's he going to label and communicate that information? Okay. So, that's fine. What if you had 10 baseballs going to 3 outfielders? Well, a lot of them are going to hit the ground. They're not going to catch them all, but the danger is they won't catch any. Okay, you can see how that might happen pretty easily. What's happening at this stage of the game is the players become overwhelmed with the communication problem. What in the military business and other business is called the command and control problem. How do you communicate the necessary information to know how to coordinate the actions of the players? Okay, so got 10 baseballs coming, put 10 outfielders out there. Suddenly the problem is not simpler, it's harder. because you got 10 guys trying to talk to each other instead of only 3. Okay, 100 baseballs and 10 outfielders. Okay, everybody's throwing up their hands. Well, what we've got in the space surveillance business is sort of like having 22,000 baseballs and 24 outfielders being those sensor sites. That gives you some idea. Okay, it's not quite that bad, and I'll explain why on the next chart, but it's bad enough, okay? The point being, the difficulty of the tracking problem, of this type of tracking problem, where you have no prior information about where that ball might be going. All you know is somebody at home plate hit that thing out in the outfield to you. The difficulty of the problem increases much quicker than the number of balls in play or the number of guys on the field. Okay, it goes up geometrically. And that's very hard to picture if you're not directly involved with it every day, but it's a real inherent feature of space surveillance. You have to deal with this high complexity in the tracking business. Okay, it's not that hard for several reasons. One is, we've never had to build the catalog from scratch in a short amount of time. We had the first satellite go up in 1957, and since then, we've been able to add 2, 3 satellites a day, typically. A few go away every day. But over time, we've had, 40, 50, 60, almost 60 years now. 60, did I do that right? 60 years? 60 years to build the catalog up to its present 22,000 objects. Okay, so that's good. I mean, we have some hope for keeping the catalog. Another thing that helps us is satellite motion can be modeled very well. We understand the physics of satellite motion, and they're mostly not controlled in dramatic ways. So the physics dictates where these satellites are going to go. We can calculate that very accurately. Okay, that's good. In fact, that's my field. Okay, predicting satellite motion. The other interesting thing about orbital motion is that the time scale is such that it takes an hour and a half for a satellite to go around the Earth. Baseball might take, 5, 10 seconds to get to the outfield. Well, if you've got an hour and a half before that satellite comes back around, you've got time to do a lot of fancy computation and prediction and prognostication, and that has made it possible to do this job. In other words, because they go around and slow enough that you can react to it, you've got more than one chance to catch the ball. And that's what saved us to date. Now, you may remember back in the 80s, there was this big issue with ballistic missile defense, Star Wars type missile defense. That was the situation where you might have 100,000 missiles coming over the horizon all at once. It was a near hopeless tracking problem. With space surveillance, we don't have quite that situation. We have hope. We have more than one chance to catch these balls, and we do, over time, get almost all of them that are detectable by our sensors. 95% of the satellites are not trying to trick us. They don't maneuver, they don't split, they don't merge, they don't evade detection, in other words. There's no stealth satellite, at least yet. If somebody figures out how to make a satellite invisible to radar, we got a problem. But so far, no go. Another kind of technical aspect of this is that the space environment is really good in black. You're seeing these satellites against a black background. That means for most of these sensors, radar and optical alike, you have a low clutter. You're not seeing a lot of noise in the background. There's not a lot of snow in the screen. There's not a lot of false signals out there. So if you detect something, it's very likely to be a real object, okay? And yeah, there are 22,000, but there's still space between those satellites, okay? It's a low number density. If you're looking at a very small region of space, the chances are you're only going to see 1 or 2 or very few satellites in that small region of space at any one time. So there's correspondingly less chance of confusing the targets. Okay. And by the way, computers have gotten really good since 1957. Computational capacity's gone up 10 to the 6th, 10 to the 7th, more in performance, whereas the number of satellites has only gone up like 10 to the 4th. Okay, we've been able to stay ahead of it. The difficulty with the future catalog is most of those assumptions are now going to be called into question. If we suddenly turn on sensor systems that can see 100,000 or 200,000 objects instead of 22,000, now what are we going to do? We suddenly have to build a catalog in a short amount of time, pretty much from scratch for most of those objects. We have the 90% job to do, in other words. As satellites become small, they are affected by forces in space such as strange things. Solar radiation pressure, for example, affects satellites. In space, if you're weightless, even the pressure of sunlight can move the object over time. Those very small satellites have forces acting on them that are very hard to model and predict. Suddenly we can't predict satellite motion for those small objects as well as we can a rocket body or major satellite that we can do today. Still, orbital motion is just as fast as it always was. Real time in the tracking business in space surveillance means minutes, not milliseconds. It's still true that 95% of the satellites are not going to maneuver. In fact, that percentage will go up. That's some comfort, but we might have 100,000 objects. It's no longer going to be true. The space is a low clutter background. As you go to very faint optical magnitude, visual magnitudes for space objects and telescopes, suddenly the detector, your CCD camera array is injecting noise. You see a lot of false detections at this very faint end of the detection band. So small objects are seen in a noisy detection environment. It's not as black in the background as it used to be for those small targets. Also, the low number density of space objects is not going to hold. That assumption is not going to hold for places like the geosynchronous orbital belt, where we're suddenly going to see things we never saw before, and they're all going to, it's going to be very well packed out there. All of a sudden, the catalog has just grown about as fast as the computer capabilities that we've got. This is a subject of research now. We're trying to do supercomputing, parallel computing for this tracking job, and that's a fairly new thing. Okay. So anyway, future catalog is a big problem technically. How big will it be? I just threw out the number 100,000, 200,000. We can quantify it a little bit. Depends on how small a target you want to see and put in your catalog, okay? Here's an eye chart for you. I'll just discuss a couple of these numbers. This is a table of the reference population adopted for orbital debris studies in Europe a little more than 10 years ago. In fact, more like 15. This is the European Space Agency 2005 reference population. Now, I use this one. It's older. There are more recent ones, but I use this older one because it breaks out the type of object into some interesting categories that let you know what's involved here. I'll have to walk over here out of the light. Sorry. Stuff we launch into space still in the thousands, and you see the columns are bigger than a millimeter, bigger than a centimeter, bigger than 10 centimeters, bigger than a meter. Most of the catalog is like right here right now, but the reference population includes all these smaller objects, which we expect to be tracking routinely in the future. Okay, sometimes satellites explode. In the reference model of the space population in 2005, there were 6 million objects bigger than a millimeter. Remember what I said about that 1 or 2 millimeter sphere of aluminum at orbital speeds? Okay, you got 6.4 million of those rascals out there. Okay. Collisions, not too many collisions by 2005. Since 2005, we've had 2 major collisions that put quite a few thousand in this last column, or several thousand in this 10 centimeter column. This is an interesting category. Sodium potassium coolant. In the 70s, the Russians put up a whole series of satellites that had nuclear reactors on board that were cooled by liquid potassium and sodium in the reactors. When the satellites were shut down operationally, the reactor core is still there, the liquid sodium and potassium is still in there. Unfortunately, because of the design of those satellites, they started leaking liquid metal into space. And they formed perfectly spherical, shiny droplets, several centimeters in size, okay? In 2005, there were like 24,000 of those things bigger than a centimeter. The total final count by roughly 2009 or so was in the neighborhood of 70,000. And these are in low Earth orbit, okay? SRM is solid rocket motor. And look at these two lines together, slag and ejecta. Solid rockets are a very cheap way to move masses around in space. Okay, that's why they're often used for the upper stages of satellites. That expensive stage that has to work very reliably and put the satellite into orbit. Unfortunately, solid rocket fuel, when it burns, puts out tiny particles of aluminum and aluminum oxide, emery powder, if you will. And so there's a lot of these things. There's the ejecta that happens during the burn, and then when the solid rocket motor is shut down, it's got this hot fuel inside, and it puts out clinkers. Clinkers, just like an old coal stove. And the clinkers come out of the rocket casing. The nozzle is open to space, they just come out. And you get things of all size. Some of them are bigger than a centimeter, these cinders, if you will, from the inside the solid rocket boosters. In 2005, you had huge numbers of these things in Earth orbit. Now, this isn't something you can track routinely, but you can sample the population, and you can model this pretty reliably. So we have that. The total count is, and I call your attention to this 1 centimeter column. The total net effect in 2005 was there's just over 600,000 objects bigger than 1 centimeter in Earth orbit somewhere. Probably most of it in, well, it's hard to say where most of it is, even according to the NASA model, or the ESA model. 600,000 is a lot. We're going to have sensor systems that can see not quite down to 1 centimeter reliably, but several centimeter scale objects. So we're talking hundreds of thousands of targets in the catalog in the future. Okay, you can just let your imagination run with that. Here it is. Here's the same information in graphical terms. If you're not used to looking at log-log plots, this is a logarithmic scale of size, logarithmic scale of total numbers. Log-log plots can fool you if you're not onto them, okay? This is tremendous increase of numbers of objects at small sizes. Tremendous. If you were to plot this on a linear scale, the graph would go like this. Okay, and I have a sketch of that later in the briefing. How hard to build the catalog. Okay, I've given you the baseball analogy. It says, boy, this command and control problem could be something. How are we going to do it? How are we going to make that work? Well, okay, currently we've got maybe 22,000 objects. What that means in practical terms is the Space Surveillance Network gives us about 275,000 observations per day. That's radar measurements, optical telescope measurements, all added up. Well, if only a few thousand of those turn out to be from telescopes nowadays. In the future, with 100,000 or more objects, we're talking about a few million observations per day. And we could have a big boatload of telescope observations. Now, why does that matter? Well, our catalog is most incomplete out there in that far region of space beyond low Earth orbit where only telescopes can give us the information. Okay, so we're going to be highly dependent on those optical observations, those optical telescope observations. We're talking about, at the moment, the volume of space out to the geosynchronous orbit is 50 times the volume of the space inside the radar surveillance reach. Okay? If you want to go out to 100,000 kilometers altitude, where the most distant satellites are that we have in the catalog today, we're talking 750 times that radar volume. The optical observations are going to be very important in the future, and that's why we're pedaling as hard as we can in our shop here at AFRL in Maui, because we're doing optical space surveillance. We're trying to understand how to proliferate these systems so that we can make the best use of them. Okay, in low Earth orbit, most of the orbits are circular, relatively easy to predict in that respect, although atmospheric drag causes issues. But out in that optical surveillance volume, that medium Earth orbit and geosynchronous orbit. There are satellites that are highly eccentric, very hard to track, very hard to find, very hard to find again if you can find them once, that kind of thing. So the most interesting parts of space surveillance are going to be in that optical surveillance regime. Here's another reason why. If you have a radar, you're measuring range to the target because you send a pulse out and time how long it takes to get back. It gives you range. And you've got two angles that you can get because you know which way the radar beam is pointed. Okay, so that's good. If you want to compute an orbit, you need to get three components of position, x, y, z of position, and the x, y, z of the velocity vector, too. I said the word vector, don't panic. You need 6 things. You need to measure 6 things to compute an orbit. If you're using a radar sensor, you can measure 6 things with 2 pings. You get a range and an azimuth and an elevation angle for one hit, and a range and an azimuth elevation angle for another hit. That's 6 things you just measured. And with 2 radar returns, if you will, you can compute an orbit. Now, it won't be very accurate. You'll have systematic errors and stuff, but you can start the job. Okay, you can start the job of tracking it in the future. If you have an optical sensor, by the way, this is our 3.6 meter telescope on top of Haleakala here, and I couldn't resist, using that as the background, the eye candy, if you will, for this chart. If you measure with a telescope what you can measure about a satellite, you can measure 2 angles. Okay, in the astronomical terms, it's right ascension and declination. Sometimes azimuth elevation, depending on how the thing is designed, but essentially 2 angles. Well, if you can only measure 2 angles on one observation, that means you're going to have to make 3 observations to get 6 things so you can compute that 6 component orbital information that you need to compute just to get the process started. Okay, that's not bad. What that means is, if you have a radar and it tracks an object, sees an object here, and then it sees a lot of other stuff at later times, your job as a space surveillance analyst is to figure out which one of those things this original observation went with. And you're going to have to go through this batch of observations. Remember, the satellites aren't telling you what they are. There's no identification, friend or foe, as there is in the aircraft business. We're talking just tracking. All you see is blips, and you got to put them together. So to put them together, you've got to run through all the combinations of n number of observations, taken 2 at a time. N choose 2 in the parlance. Okay, now, so that adds up to the number of hypotheses, the number of trials you have to make to figure out what the real orbit is like n squared. Okay, and your computer's going to be grinding a lot longer for 1,000 of these things than it is for 100 of these things, but you can do it. If it's only n choose 2 kind of complexity in this processing, you can do it. And we've done that in demonstration here on Maui. We've speeded up the overall process for existing methods by a factor of 100, and we can do it with 400 processors, and we can process hundreds of thousands of observations. We know how to do this radar problem. We know how to do the n squared problem. But wait, I said we're doing optical space surveillance. If you need 3 observations, and you got to run through all combinations of n observations taken 3 at a time, that's a much different proposition. For example, if you have 10 observations and you're going to take them 3 at a time, that's already 120 things you've got to check, 120 trials you have to make to see which of those orbits is the real one. If you have 100, you're up in 161,000 trials that you've got to run through to find the right orbit. If you've got 1,000 observations and you got to take them 3 at a time to find out what the real orbits are, you got 166 million things to run through and try out. This goes up dramatically. This n choose 3 problem is really bad. Now, there are other methods for computing that initial part of the orbit determination process. Some of those methods use 4 observations instead of 3. Okay, well, that only makes the problem worse. If I got 1,000 observations, I got to take them 4 at a time. That's 41 billion. It's unfeasible. Okay, it grows too fast. We're expecting in the future between 10,000 and 100,000 observations per day on objects we've never seen before. Okay, how the heck are we going to do that? It's safe to say this is a matter of research at the moment, okay? And if we had to do this tomorrow, our goose would be cooked. It would take many years, okay, even with the best computers available. Here's another aspect of that tracking problem. Remember, we had that log-log plot that was sort of a gentle slope, but if you plot it in a linear scale, here's that linear scale of target size and number of targets. It's just a cartoon, and I see this one didn't display exactly right. Let me see if it comes back. No, okay. Here's the situation. This is the size distribution of the number of the satellite population in space. Out here, we're talking 10 centimeters to a meter in size. Down here, we're talking few centimeters in size, or down here next to the origin, off the scale for millimeter-sized objects. Safe to say we're not going to be tracking millimeter-sized objects routinely for many years. But here's the situation. If we're out here and our detectable target size varies a little bit throughout the space surveillance network because of environmental factors. Sometimes the air is less transparent than at other times. Sometimes the radar circuits are a little noisier than at other times. There's all sorts of environmental reasons why our sensitivity might vary over time. Out here, if the sensitivity varies a little bit, you don't change the number of targets in your catalog very much. You're still seeing most of them most of the time. Maybe a little bit. Right now, the slop is less than 1 or 2% in the total catalog count, just due to variability in the sensitivity of the detection systems. Down here where we're going, in the few centimeter range, the number of targets is not only very large, but it's a steep curve. That means if your sensitivity varies just a little bit due to environmental effects or whatever, suddenly the number of targets you can detect changes a lot. Okay, go from here to there, move over an inch and go to there. Suddenly you've got a big band, a big change in the number of targets. So that means for those small size objects, you don't even know how many of them you've got in track. You don't even know how many of them there are. Over time, you can get a statistical average, but you really don't know on any day how many you've got. How are you going to keep a catalog if you don't know how many you've got? You need to track that centimeter, 1 to 2 centimeter, 1 to 3 centimeter size stuff if you want to protect manned spaceflight in the future, other satellites. The space station, for example, is shielded against debris strikes for objects up to a centimeter, maybe a little bit over toward the 2 centimeter size. But it's not shielded everywhere. Only the critical parts of it are shielded with these bumpers, so-called bumpers. Well, if it's bigger than a couple of centimeters, you got to track it and you got to get out of the way of it in time to keep from getting hit by it. Otherwise, it comes right on through. Okay, that's down here in this bad regime where you don't even know how many of them you've got, even if you've got the sensor systems that can detect them. It's a real problem. That's part of the research effort here. How do we deal with the uncertainties here in a case like that? Very difficult. My conclusion, if you can't tell, I could talk all night on this subject. I'm wearing you out. I see eyes closing. So here we go. Why do we need a satellite catalog? Well, I gave several fundamental reasons. I think even my 2-star general got it that day, okay? And here we are today. We're still in business. How big will that catalog be? Safe to say it'll be an order of magnitude larger than what we've got now. And it won't build up over 60 years. It'll build up overnight, okay? So how are we going to do that? How are we going to react to that without losing? I mean, how are we going to catch all those new balls without dropping the ones we've already got? Okay, that's a good question. How hard is it going to be to build that catalog? In computer science terms, we're talking about polynomial algorithmic complexity. N choose 2, N choose 3, low-order polynomials. Now, in the computing business, that's considered fairly benign. Polynomial complexity is fairly benign. We think we can do that. The problem is you don't do that with a problem size like the space catalog. You don't do it with 200,000 targets and, up to between 5 and 10 million observations per day. You do it with smaller problems than that in a computer science sense. So we're going to have to figure out, even though it's polynomial complexity, it's not an easy job, and there's still research that needs to be done in that area. Okay? So I leave you hanging with that. That's the end of the talk. That's for you to meditate on, if it not keep you awake tonight. Okay? Yes, in the back, yes. Yes. Yeah. Here's why that's a bad idea. If remember what I showed you on that chart with the radar reach, the reach of radar. You can go out 5,000 kilometers or so. In orbit, 5,000 kilometers buys you a few seconds, maybe a couple of minutes. It's too late. By the time you detect something from the size of a radar you can afford to put in orbit, by the time you detect it, you're already in trouble. Okay? That's the problem. There's no Battlestar Galactica solution to this kind of problem. Yes, sir. Yeah. Yeah. Only U.S. satellites. U.S. operators are required to divulge that information ahead of time to U.S. Stratcom. Yes. The question was, what percentage of the satellite launches do we know any advanced information about? Because it's much easier to track if you know where this thing's supposed to go. And the answer is, in fact, we only know U.S. launches, and so we have to wing it with foreign launches, and that is a big deal. Yes, over here. Yeah, you just destroyed your communication environment because you depend on low power communications to be efficient in space. You had a follow-up with it? Still a substantial fraction. Now there are a dozen or so routinely spacefaring nations. The question is, what percentage of launches are U.S.? Thank you, JD. You're going to have to do that again in a minute. The thing is, between the U.S. and Russia, and now China a little bit, we've got almost all the launches covered. Okay? So the problem is Russia and China don't feel it necessary to notify us when they're going to launch, what they're going to launch, how many things are on that booster, et cetera, et cetera. That's why the surveillance job is still a military mission. Yes, in the very back. That's a good question. Right now, the question is, what will improve our capability to detect small objects? That's a profound question. That's another talk. But I'll tell you the short answer. I've been alluding to the new sensor acquisition programs that are coming online 5 to 7 years. One of them is an optical system that can see, under ideal circumstances, we'll be able to see golf balls, okay, in geo. Another is a radar system that will have not the typical UHF band wavelength, few decimeters here, but it will have an S-band, so-called S-band, about 3.5 centimeters wavelength. You can see quite small stuff with that kind of radar wavelength. The reflected power is not great. It takes a really corking good receiver to pick it up, but you can do it, okay? And that's why I've been saying we can see objects on the scale of a few centimeters a few years from now. But that's also the reason why here's the problem. Very difficult to build a radar at 3.5 centimeter wavelength or 5 centimeter wavelength or whatever it finally ends up being. You cannot see that stuff. You're going to see it on day one. Now what are you going to do with it? That's the issue. Okay. Yes, sir. Yeah. Jeff is asking the question of about the so-called debris chain reaction process in space, where if debris objects start hitting each other, they create more debris. Those objects go on and hit other things, create more debris, and it's a cascade effect. And in fact, you're paying compound interest on that growth, okay? This is exponential growth. It turns out the effect is real, but the time scale of it was wrong. The estimates they were using back in the late 80s, early 90s, and I know the gentlemen who were doing it at the time, and they're pretty sharp guys. Their traffic models for the future introduction of mass into space and the sizes of objects into space that they were using were wrong. They didn't pan out. Instead of several decades kind of time half growth, you have several centuries in the current scheme of things. The effect is real. This will happen in low Earth orbit, and it will be hard to get a spacecraft beyond low Earth orbit without getting hit by something. But that's centuries away. In the meanwhile, there's hope that maybe there are ways to clean it up a little bit, enough to keep it from overwhelming us. That's correct. The gentleman points out this process is called the Kessler syndrome after Don Kessler, who was at NASA Johnson Space Center in the late 80s, early 90s. And naturally, a lot of his projections depended on the space catalog. I was one of those guys, one of those engineers helping keep the space catalog in those days, and so we ended up spending a significant amount of time with the NASA guys, including meetings at the Pentagon where the NASA guys were saying, this is going to happen in 20 years, and the DOD is saying, so what? Okay, and it was a real hard meeting of the minds, but finally it just didn't pan out. We're here today, though, with a known physical effect that if we don't control it, will eventually get out of hand and not be fixable. So there's a lot of interest in reducing the amount of debris that's created in space. And the answer is remove those big rocket bodies that are just floating around up there empty. Get them out of the way. Okay, and that's the short answer. Yes, sir. It's about 22,000 miles altitude. No, low Earth orbit goes out to maybe 500, 800 miles. I mean, it's miles, kilometers. The low Earth regime for surveillance goes out to 5,000 kilometers by just general agreement. There's no hard boundary there. Above that is just medium Earth orbit, and geosynchronous is out at about 6.6 Earth radii from the center. Low Earth orbit's about 1.1 from the center. And so that's the difference in altitudes there. Yes, ma'am. Indeed, there are. In fact, there are companies proposing to make money doing such things. Okay, they're trying. Now, the problem is there's no panacea. There's no one method that's clearly going to work. The problem is a 1 pound trout. Okay, right? Who's going to catch that 1 pound trout without making a mess? That's the problem. Now, if you can't do that, what are you going to do with a rocket body that's 10 or 15 tons? So there you go. So that's the yes, ma'am. Yeah. The question is there anybody else besides the United States involved in this cataloging business? The short answer is no. The medium answer, the long answer is really long. The medium answer is that Russia does keep a catalog using their own resources. They periodically share that catalog with several different U.S. agencies. They always have a few dozen to 100 or so objects that we don't have in our catalog. But basically, theirs isn't much good, and it's getting worse because of the budget situation in Russia. They're shutting off sensors. China does not do a catalog. China is currently in the mode of believing they can track only the satellites they're interested in to do what they want. Well, they'll find out different, but right now, they're not materially playing in the space surveillance business. The European Union, the European Space Agency, a consortium of probably 15 or so European countries, is working hard to develop a European-only space surveillance system, global coverage, and doing it for European purposes. The problem is, if you think U.S. bureaucracy is bad, the bureaucracy in the European Union is really bad, and besides the budget problems in Europe. And that means that, in effect, they've got a lot of great ideas. I wish we could get together with them and work on those ideas. But right now, the game is in the U.S. Yes, sir. Yeah, the question is, and thank you, Joe. The question is, isn't it feasible and maybe even a good idea to put some fairly powerful radars, a few fairly powerful radars in orbit to monitor this population that we can't really see from the ground very well? Yeah, that's right. You could put these radars in GEO and see the small objects out in GEO that you can't see from the ground at all. Just reduce the range. That's one way to solve a radar problem. Get the radar closer to the target, you can do the job. Well, and there are lots of schemes. The answer is that indeed a lot of proposals like that have been made. The question boils down to economics. Okay, it's sheerly economics. We have the technology, we don't have the bucks. And this could be done feasibly, yeah, but it's not economical. Now, what is economical is to put telescopes in space for space surveillance purposes, and right now there is one. All right, an operational surveillance sensor that's not on my map of the world because it's in orbit, low Earth orbit, and it can from low Earth orbit it can see the entire geosynchronous belt every day, and it's being put to good use. Okay, it's called SBSS, Space-Based Space Surveillance System. Unfortunately, budget canceled the follow-on, so there's one of these things for the next predictable amount of time. But putting telescopes in space is a much more economical proposition, and probably we'll end up with lots of surveillance telescopes in GEO and probably on some highly elliptical orbits to cover the MEO regime. That actually might work out in the next few years. I'll talk all night, folks. Just keep asking questions. I'll stand here till I drop. So, listen, thank you very much. You've been a really good audience. I certainly appreciate it. Thank you.